All right, now that we've talked about the five-step method, I want to do a more complicated situation involving a slightly different choice of coordinate system. Surprisingly, and you guys all know this, the world is not flat. We often need to do physics in a situation where we're not on level ground, so we need to be able to adapt our five-step process to be able to do this. First example I'll give is an inclined plane. Very famous, very common example, you'll see it a lot. You can set up this problem using the five-step method, and then we should be able to discover some relationships and equations that will always be true for things on inclines. We'll do most of the problem in general, meaning that I'll use variables instead of numbers. There's an advantage to this. In doing so, I will solve the problem for all masses and all angles. So, consider a box of mass m and an inclined ramp of angle theta. First, we'll consider the incline to be frictionless. Step one, I draw a picture. There's my picture with all the forces identified. I've got Fn, I've got the weight down, there's mass, and then there's an angle. It's not a great picture, but the picture is good enough to give you an idea. Step two, I have to ID all the forces. In this case, as I said before, there's two forces. I have the normal force, which acts perpendicularly to the ramp. Remember what normal means. Normal means perpendicular. And then I have W, the weight, which acts directly down. Step three, I have to define a coordinate system. Again, I'm going to have a choice here. We want to pick the coordinate system so that the motion of the box is in either the X or the Y direction, but not both. In doing so, that's going to make the math a little bit easier. How will the box move? The box should slide down the incline. That's the way things want to normally go. So I'm going to define one of the directions to be along the direction of the ramp. The second direction will be perpendicular to that. So here's my picture I had from before. My positive x will be down the incline, and my positive y will be perpendicular to the incline. It'll look something like that. I call this the slanty coordinate system because it's slanted at the same angle as the incline. In 3B, step 3B, I have to do trig. The normal force is along the y direction, so it's okay, but I am going to have to do trig on the weight. Here's how I'm going to break it down. I'm going to have W cosine theta in the negative y direction and W sine theta in the positive x direction. Notice that my W forms the hypotenuse of a right triangle. The W sine theta and the W cosine theta added together give you the weight vector like we did. Step 4, I have to write N2 for all the directions. When I write my equations in step 4, all the motion will be in the x direction. There's going to be no motion in the y direction. My box isn't flying off the ramp. So in the x direction, I get W sine theta is equal to ma sub x. And in the y direction, I get Fn minus W cosine theta is equal to ma sub y, but that's 0. As I said before, my object is not flying off the ramp. You also should remember that W is going to be mg. I'm going to use that in the next slide. Finally, step 5, I have to solve the equations. No more physics to do, just some math. First, I'll substitute mg for W in our equations. So, my x equation becomes mg sine theta equals ma sub x. If I solve this for a sub x, looking at the math, mg sine theta equals ma sub x, masses cancel on both sides, so I get the acceleration along the direction of the ramp is just g sine theta. This is a general result, and it's a very significant result. For a box of mass m on an inclined plane of angle theta, my acceleration is going to equal g sine theta. Notice the mass doesn't matter. Again, it's a general result, and usually when I do things in variables, I want to see if extremes make sense. The smallest angle I could have would be 0 degrees. In other words, our ramp would then be a flat surface. Putting 0 in the equation gives a sub x to be 0 meters per second squared. That should make sense. An object sitting on a flat surface is not going to slide either way. It's just going to sit there. The largest angle wouldn't be 180 degrees. It would be upside down at that point, but 90 degrees. That makes my ramp into a vertical cliff. If I put 90 degrees into the equation, that gives a sub x is equal to g. In other words, it's in free fall. My object would be like falling off a cliff. Something falling off a cliff would accelerate downward. In this case, my x direction would be downward at g. Because the two streaming values of 0 and 90 degrees seem to work and seem to give correct answers, we can expect rationally that any value between 0 and 90 degrees would also give us a correct answer. Now, let's consider the same problem, but I want to add friction to the situation. You have a box of mass m on a ramp of incline theta, but with friction. The coefficient of kinetic friction will be mu sub k, and the coefficient of static friction would be mu sub s. Here's the drawing I had from before. Step 1, I draw the picture. Step 2, I'm IDing all the forces, but now I have to add the frictional force. There's the arrow for friction, and there's the name that I call it. Friction acts up the ramp because friction always opposes motion. The box wants to slide down the ramp. Friction opposes that, so it's directed up the ramp. There's the coordinate system I'm going to have. Just like I did before, it still makes the most sense. I still have to do the same trig from before. Fn and the frictional force are along the y and x directions. W is the one I have to do trig on. I do the W cosine theta and the W sine theta like before. Everything looks right. Now, in step 4, I've got to write N2 for both directions. The y equation is going to remain the same, but it's now the x equation that's going to change. In the x direction, I get W sine theta in the positive x direction, but it's opposed by the frictional force, so that's why I have the minus F sub F. That's got to equal ma sub x. My y equation is the same. Normal force minus W cosine theta is ma sub y, but that's 0 because my box is not flying off the ramp. Again, remember that the weight is always going to be mg, but now I have the additional constraint called the frictional constraint, so that the force of friction is equal to mu times F sub n. It could either be mu sub k or mu sub s, depending on whether or not my object is sliding or not moving at all. Finally, in step 5, I can solve for the normal force, and then the frictional force, and then a sub x. First, the y equation. Fn minus W cosine theta is equal to ma sub y. That's equal to 0. I can solve this for F sub n. Remember, the frictional constraint relates the frictional force to the normal force. So the y equation, or at least one of my equations, will involve the normal. I need to solve for that. Using the frictional constraint, I find that the frictional force is going to be mu sub k mg cosine theta. I've picked mu sub k because I'm going to assume that my object is going to be sliding down the incline. Now I can do the x equation. F sub x gives me the equation of W sine theta minus the frictional force is equal to ma sub x. Substituting mg for W, I get mg sine theta minus the frictional force is equal to ma sub x, and then I substitute for the frictional force. So I get mg sine theta minus mu sub k mg cosine theta is equal to ma. Notice that mass appears in all three terms, and so it will cancel out. Mass is irrelevant in this case. Simplifying my expression gives me a sub x is equal to g times the quantity sine theta minus mu sub k cosine theta. This is the general result for an object of mass m sliding down an angle of theta with friction. It assumes that the ramp is steep enough so that the frictional force does not stop it from sliding down. We do need to talk about that, and that'll be in my next slide. Again, if I put in the extreme values of 0 degrees and 90 degrees, they do work. On a flat surface, if there is no applied force, then there is no frictional force opposing it. That effectively makes mu sub k 0, so that makes my a sub x to be 0 meters per second squared again. Again, an object sitting on a flat surface, even if it is rough, isn't going to move. On a cliff, if I make it 90 degrees, cosine of 90 is 0, so then a sub x, in this case the downward direction, is going to be equal to g. Now, last thing to do is consider the same problem, but now the box isn't moving. It's stuck. In fact, we're going to say that the incline is tilted just enough so the object is just getting ready to slide. So that way we'll be able to find the maximum coefficient of static friction. So in this case, my a sub x is going to be 0. It's not moving. And I'm going to replace my mu sub k with a mu sub s. We had this equation, and it becomes this equation. 0 equals g times the quantity sine theta minus mu sub s cosine theta. I can do a whole bunch of math and to solve on this. Notice that the g is going to cancel out, and I get that the tangent of theta is equal to mu sub s. Make sure you understand the math I did there. Notice that sine of theta divided by cosine theta is just tangent of theta. So if I solve for mu sub s, I get the famous result that mu sub s is equal to the tangent of theta. This is the general result, which tells us the maximum coefficient of static friction for an object on a ramp just before it's beginning to slide. As I increase my angle, my theta becomes bigger. That means tangent of theta becomes bigger. That means my mu sub s becomes bigger. Eventually, it's going to start to slide. This is how scientists called tribologists, tribology is the study of friction, measure the coefficient of static friction. You place an object of a known material on another surface of a known material, you adjust the angle until it finally starts to slide. At that moment, you measure the angle, you take the tangent of that, and you get the coefficient of static friction. This is an empirical measurement, meaning we have to measure it by science, by actual experiment, not by a value that we can calculate. We really don't know how to calculate coefficients of friction yet. Hopefully this clears up some of the mysteries of inclines, and you should be able to do problems on surfaces that are not flat.